Okay, students, so I'm recording. I think I'm the only one in the room, and I've hidden the video. I'm sharing my screen, and I've hidden the video panel, so you can only hear me right now. Just wanted to show you how much I know about Zoom. Anyway, okay, so students, we have this is our last week before spring break, and I don't want to start a new. The next topic normally would be something called heap sort, which is kind of takes a while to present. And so what I'm going to do is and then, the next, and I don't really want to give you a quiz on that on Wednesday. And then the next opportunity after that would be 2 weeks from today. You do know, so I did post a quiz today, due Wednesday. It's 4 problems, no programming. And then I'll post another quiz on Wednesday, due Friday. And it should be relatively, I think, not really a lot of programming. Hopefully it's something everybody could do. And then your assignment due Saturday, and then we have a week off. So I wanted to talk about these topics that, I was saying, what could I talk about today? I could give you a quiz on them on Wednesday. And then, so what is this kind of just Java program, nothing to do with algorithms, but it's how to reduce the number of multiplications when we're in a loop. So let me just show you here. So I'm sharing the screen here. Let me just show you the problem here. And so I'm activating. So I had this open already. So let's say we wanted to, first of all, let me just scroll up here. I might have some stuff written from before. I have a hard time finding my mouse. Okay, so if you can read my writing here. Okay, so so at some point in the course, at the beginning of the year, I think we get a quiz where I asked you to display multiples of 4, no, powers of 4, powers of 5. And so here are 2 solutions. And so the one on the left, the one I labeled the good solution, there's 1 multiplication per iteration. So the number of multiplications is essentially grows linearly with whatever the exponent is. Here the exponent is, we're going up to 5 to the 5th. The exponent is 5. So the number of multiplications is 5. Now let's look at that other one. And here, see how we're using math.pow to calculate 5 to the I, like 5 to the first or 5 to the second. And here's why I don't like it. First of all, just remember math.pow does require us to cast if we want integers. But the other thing is that, okay, so let's say at I equals 4, math.pow is going to calculate 5 times 5 times 5 times 5. Okay, 3 multiplications. The number of multiplications is always 1 less than I. But let's say then we get to I equals 5. Then now we're calculating 5 times 5 times 5 times 5 times 5. So why do we have to calculate 5 to the 4th again? We just calculated in the previous iteration. Why not save that and use it for I to the 5th? And that's what when you go math.pow, we're not doing. We're not saving the result of the previous calculations. We're just throwing away those calculations. And that kind of, for our little programs, no one's ever, will never notice because there's so few floating point operations. But, if your program is running a long time, you want to reduce any kind of unnecessary calculations to make the program run faster. So here, the solution to avoid the number of multiplications is really n squared. It's an order of growth is n squared. Because when I is 2, it's 1 multiplication. When I is 3, it's 2 multiplications. And when I is n, it's n minus 1 multiplications. And then there's that famous formula, 1 plus 2 plus 3 plus, so forth, all the way up to n minus 1 is n minus 1 times n over 2, or it's order of growth n squared. Okay, so the number of multiplications for the good solution is, the order of growth is n. The number of multiplications for the bad solution, order of growth is n squared. Okay, so let's just see how we can do this in a couple of problems. And so here's problem 1. I have it circled. So we want to write a method that finds that sum. 1 minus 2x cubed plus 4x to the 6th plus 8x to minus 8 to the 9th and 16x to the 12th. And students, we cannot use math.pow. Just forget about that even exists for right now. Or we can't write our own math.pow. So there's no workaround. So I say don't use math.pow. Don't write your own method that does a similar calculation. Okay, so let's actually, so now we'll go to, hello. We'll go to, actually I wrote out the code for the first one. Okay, so method 1. So let's just see how we do that. Okay, so there's the comment there. And So we want to return 1 minus 2x cubed plus 4x to the 6. So it's an alternating series. No, sequence. Yeah, no, alternating series. Yeah, it's a series. It's a summation. 1 minus 2x cubed plus 4x to the 6 minus 8x to the 9th plus 16x to the 12th. Alternating because it's alternating. The terms are alternating in sign. And note, okay, so so all these methods, all these examples will use this, we'll have this pattern. I'll initialize the sum. So the sum starts out at 1. The first term we add on is 1. That's the constant term. And then I add on what's called the base. And so that'll be the term after 1. It's minus 2x cubed. Now, what do I multiply to get to the succeeding terms? Like to get to 2x cubed to 4x to the 6. I'm sorry, the base is minus 2x cubed. Once again, we multiply. It's the same as we multiply by the base. That's by coincidence, right? So to get 4x to the 6, you take the base, which is minus 2 times x times minus 2 times x times x times x, and you multiply it by minus 2 times x times x times x, and you get 4x to the 6. Now, how do you get 8 to the 9? Minus 8 to the 9th from 4x to the 6. Well, you multiply. You have to put a minus there. Once again, you take 4x to the 6th, it should be a 6 here, and you multiply it by minus 2 times x times x times x. So I have these 3 variables that I'm declared sum, base, and multiplier. The sum is 1, the base is minus 2x cubed, and then the multiplier is also, just by coincidence, minus 2x cubed. So there's 4 terms after 1 that we have to add on. So we start with the sum. So the sum is sum plus base. So after first iteration, it's 1 minus 2x cubed. Right, so after iteration 1, sum is equal to 1 minus 2x cubed. And then what we do is we multiply, okay, after iteration, then we multiply the base by the multiplier. So after iteration 1, okay, the base is now 4x to the 6. And then we just add 4x to the 6. And then we just add that on, right? So then we go up, we do another iteration, and we'll add on 4x to the 6th, and then multiply the base by minus 2x cubed. We get minus 8x to the 9th. So that's all there is to it. So let's just try another problem here. And let's try this one right here. Okay, so, and there's 6 terms there. 1 minus 3y squared minus 3y to the 4th minus 3y to the 6th, and so forth. And we're going to call that method 2. And so I'm just going to copy and paste, even though you're not supposed to do that. This is what leads to error, is what I'm doing right now. Let's make sure we change everything. The error is that we copy and paste and we leave old stuff that's not really relevant to the problem. Okay, well, the variable is y. The sum is 1. And now the base is 3y squared. Whoops, 3y squared. Hello, 3 times y times y. And I guess I could use math.pal here. Don't forget to cast it. Now, how do we go from, what is that multiplier? How do we go from 3y squared to 3y to the 4th? Or how do we go to 3y to the 4th to 3y to the 6th? We're multiplying by y squared. Right, so the multiplier is just y times y. And so now the sum, oh, now it works perfectly. Now how many terms do we have? It's 6. So the number, so I less than or equal to 6. And I think this will work, right? So after iteration 1, the sum is, it's 1 minus 3y squared. And after iteration 1, the base is minus 3y to the 4th. Okay, so let's just do the next one. And the next one, yeah, so the very last one is 1 plus 6x squared plus 12x to the 4th plus 24x to the 6th, so forth. There's 5 terms. And notice, how do we go from 6x squared to 12x to the 4th? We're multiplying by 2x squared. Like how do you go from 24th x to the 6th to 48x to the 8th? You're multiplying by 2x squared. So the terms grow geometrically. And so again, well, we can just use this trick right here. Now I'm cutting and pasting again, which you're not supposed to do. So yeah, I'm really trying to teach you some bad habits here. You know, don't do this. See what I'm doing? Don't do this. If you did this at work and you made a mistake, your supervisor, whoever you report to, would be very unhappy with you. If they knew that you made a mistake by copying and pasting it, it doesn't go over well. Okay, so the base in this time in this case is 6x squared. Okay, and what's the multiplier? It's 2x squared. And I think we're done now. After iteration 1, it's 1 plus 6 times x, and after iteration 1, the base is 12x squared. No, it's 12x to the 4th. I'm sorry, 12x to the 4th. Well, let me fix this comment here. So it works. Yeah, for method 2, after iteration 1, no, that's right. The sum, yeah. Oh, yeah, that's right. The comments for method 2 are correct. Okay. Okay, so actually, I think there's maybe even, I hate to say things are easy, but this is even a little easier than I thought. Yeah, we just found the sum, we have these 3 variables. And then we just changed them depending on we looked at the sequence in the problem, and then just made sure the sum, the base, and the multiplier were set to the correct values. The thing is to notice the pattern. These are all these 3 problems, they're all geometric sequences, meaning we go from term to term by multiplying by the same term each time. Okay, so once, if you can see the pattern in the sequence, or in the terms of the series, then it shouldn't be too bad. Solving the problem really shouldn't be too bad. So there'll be a couple of these on our quiz on Wednesday. Okay, so this is the only programming that we'll have here. So I'm going to save this. And then, no, I'm not. Wait a minute. I'm going to cancel it. I do want to say I want to keep this open here. Because eventually we're going to get to a binary search. Yeah, so we're going to talk about this. Basically, that's all we're doing. The 60. It's not really. I'm not really that popular. It's all kind of notifications. Okay, so one text message an hour doesn't exactly make me popular. Okay, so let's see here. Okay, so students. Okay, so let's see. What are we doing next? Binary search. So this is not a binary search. We're going to talk about binary search trees later in the course. And we're just, as soon as after we do heap sort, then we're going to do then we'll start the searching. We'll start with binary trees, and maybe we'll even get a chance to do. We'll see how it works online. Balanced binary trees. They might be too hard for online, but we'll see. Anyway, we have a lot of time to do interesting things after we come back. We'll have 13 lectures and plus a lecture for the quiz. Okay, for the midterm. Okay, so midterm 2. Okay, but let's talk about binary search. So I do have some slides here, and then we'll do a couple of the worksheet problems. And so then the quiz problems will be similar to the worksheet problems. Binary search, the famous binary search problem. I like this. It's kind of accessible. So I think if you're interested in computer science and you're interested in algorithms, this is a relatively, I think it's accessible. So I would encourage you to try to, if you're having a hard time with this, I definitely would encourage you to try to understand it. You can always talk to me. Okay, so let's say we have the sorted array here. And that's the one thing about binary search. So you should be seeing the sorted array, and if the array is not sorted, then this does not work, okay? And remember, here are just integers. We can sort objects too. And then, the object, the sorting is based on whatever the compare to method tells us is bigger or smaller. So we want to return, we want to find is 400 in this array, and if so, return the index. We're not returning true or false. So if 400 is in there, let's find the index of 400. And if 400 is not in there, then let's return -1. And I think this array has, so this actually is, so I think this is actually I equal to 10. 400 is at I equal to 10. There's 12 elements in the array. Okay, so I is at, okay, so let's see how the algorithm can work here. So, okay, so one way we could do this, if I, math 130, we might just start right at the beginning, start at position 0, and just go one by one. Start at 0. Oh, is it position 0? No. Is it at position 1? No. When I is 10, we'd actually get flag as true, and then our code not flag would, not true is false, and the loop would stop. So potentially it's an order n algorithm, right? You might have to look at every, if the value is not in the array, you are looking at every single element, and then you're returning -1. So flag is, I wonder if this is right. Flag is, oh no, that's right. Flag is true. Yeah, flag is true. Subtract 1 from index. That's right. I know why I was getting thrown by that. Right, because if flag is true, we're still incrementing by 1. So if the flag is true, yeah, we want to decrease the index by, yeah, we want to set the index to be I-1. Okay, so now I can never find my cursor, so I'll just use my pen to move the slides. Okay, so basically here's the binary search algorithm. Okay, so we're looking for 400. Actually, I haven't really said what mid is. Mid is actually the middle index of the array. So if there's 12 elements in the array, the last index is at position 11. So we'd find the average of 0 and 11, which would be 5. Okay, so basically we're asking ourselves, so we can do this because the array is sorted. So what we're going to do here is we're going to start in the middle, which is 15, right? That's position 5. So 0 plus 11 over 2 is 5. So we start at position 5. That's mid. So that's always called mid. And so then there's these 3 cases here. Okay, so we might just be lucky, and that array of mid is actually, we actually found, because in our problem we're looking for 400. So, okay, so maybe array of mid or array of 5 is mid. And so then we're done. Okay, the other possibility is AR mid is greater than what we're looking for. Like in this case, AR mid is greater than 400. Well, everything to the right, if this is true, if this Boolean expression is true, case 2, then everything to the right of mid has to be greater than 400 because the array is sorted. See, in this way, we can actually eliminate the left side of the right side of the array, as all the terms on the right side of the array cannot possibly match 400. Okay, then if this case 3, if AR mid is less than 400, then everything to the left of mid also must be less than 400 because the array is sorted. So we can actually just eliminate everything on the left side and just look on the right side. So every iteration, we're just eliminating the remaining terms by half. So let's say the array was, let's say, like 2 to the n. So let's say the length of the array was 2 to the n elements, a perfect power of 2. So that means, okay, let's say we're searching for something and it's not in the middle. Okay, what we can do, we can actually eliminate half the value. So the remaining values, there's 2 raised to the n-1 values left. So every iteration, we're dividing the number of remaining elements by 2. And so basically, it's going from, so if we started like 2 to the n, then iteration 2 would be 2 to the n-1. And eventually we might get down to an array to size, 2 to the 0, right? So it's about, so at most there's n iterations, right? If we can't actually find it, if this element is not in the array, yeah, it'll take about n iterations. I mean, where n is actually to log of, in this case, n is the exponent, but it's a log n algorithm. So the number of iterations is about log of, or the array length. We're going to see that. We're going to do some worksheet problems, and we'll see that's the case. Okay, so students, let's just look at the code. for integers, okay? But this, we can actually convert this so it also works for objects as long as it implements the underlying algorithm, and as long as it implements comparable. So we have this array, look at line 32, and I think, and I always forget how many are in there. Let's see right here. So yes, the array length. What's the array length? So that it's, let's see, it's 5, 8, 11, 12, 16. Yeah, the length of AR is 20. Okay, and so what we're doing is we're passing in the array. We're actually passing in the array length, and I'll tell you why. And then we're passing in, like on line 39, the key that we're looking for. So actually, I'm asking the user to enter a key. And then, so that way we don't have to hard code it and just recompile every time. Now, what's the point of passing in the array length? We always know the array length. We always know the array length. Okay, so let's say we don't want a array length that tells you how many elements that we're initially going to search for. So the length of the array is 20, but let's say I only want to search through positions 0 through, I only want to search through the first 12 values. You just make array length equal to 12, and that will restrict the initial search from 0 to 11, right? So that array length, that variable array length, it actually just makes it the problem, or the parameter on line 6 is called number size, yeah, and then we're actually passing in, let me start again. In the method, we're passing in the array, the number of elements, the number size, and the key, where the key is the value that we're looking for. The number size just tells you, how many, what part of the array that we're looking at. So let's say the original array, this array here on line 32, 20 elements. I'm saying if numbers of size is assigned 12, then we're only going to look in positions 0 through 11. So it just makes it a little more flexible. It allows us to search through a subset of the array, but we're always starting from position 0. And we could actually even change this, make it even more flexible, so that we're ranging from not going from 0 to searching through 0 through number size minus 1, but some index, starting at some index greater than 0. Okay, so let's look at this. But that's all that number size is. If we always know, we can always write a method that searches through easily to just take out number size, and for the purpose of this class, number size will always be the array length. Okay, but we can easily rewrite this method without number size. Okay, so we're going to have 3 variables that we're going to see in every iteration. This is important: mid, low, and high. So low tells you the left boundary of the array. So we're always cutting the array in half. So low will tell you the left boundary of the segment of the array we're looking in. High tells you the right boundary, and mid is actually the middle point between low and high. So initially, low is set to 0, the leftmost element, and high is going to be the array length minus 1. So that's assigned on line 9. Okay, because for our problem, we're just passing numbers of size will be the array length. And then, so now we have this loop, line 11, while high is greater than low, while the index of the right boundary is greater than or equal to the index of the left boundary. Okay, line 12, we calculate the average of high and low. The index is in between low and high. And now we have we check these 2 Boolean conditions. So what the if and the else statement is going to do is, so every iteration we're either going to reset low or we're going to reset high, depending on the outcome of a Boolean expression. So 13, it says if numbers of mid is less than key. Well, if numbers of mid is less than key, then everything to the left, because the array is sorted, everything to the left of position mid is also less than the key. So we'll just look at positions so that if the key exists, it has to be in positions mid plus 1 through high. Okay, so I'm sorry, let me start that again. I'm sorry, that was right. So let's say 13, numbers of mid is less than key. That means everything to the left of mid has to be less than key. So we'll look at positions mid plus 1 through high. So what we do in line 15, if numbers of mid is less than the key, we reset low to mid plus 1. Now let's say Boolean expression in line 16 was true. Numbers of mid is greater than key. Okay, so that means that everything let's say numbers of mid is greater than key, then everything to the right of position mid is greater than key because the array is sorted. Okay, so let's just look at to the left of mid. So we'll actually reset high to mid minus 1. So we'll look from positions low to mid minus 1. So if the first Boolean expression is true, the one on line 13, we reset low to mid plus 1. If the second Boolean expression is true, we reset high to mid minus 1. So all we do in this this loop is we calculate mid, and then we evaluate, we evaluate the Boolean expressions in the if and the else. And depending on which one is true, we either reset low or we reset high. Now, if by some luck, if both Boolean expressions 13 and 14 and 16 are false, that means that numbers of mid is equal to the key and you return mid. That's on line 20. Now let's say high becomes less than low. We'll see that in one of the examples. Just return -1, that means not found. Notice what, okay, since I did not write this code, it comes with the textbook. And so notice that there's multiple returns, one on line 20, one on line 24. I would not write code like this. That doesn't mean there's anything wrong with it. There's nothing actually wrong with multiple returns. Just for this course, I'm asking students not to do it just because I think it just encourages more rigorous thinking if you just do one return. I also don't like returns in while statements or for loops, but that's just me. Okay, so okay, so students, should we do some of the problems? And I think I'm hearing a lot of people say yes. So we're going to do 3 binary search problems here, and I think I erased everything. I was working on this earlier. Okay, so yeah, so let's go away. Let's do a couple of integers. Let's do 1 integer and 2 strings. So students, notice there in problem 1, you have an array. That array is length 17, and it's sorted. And what we're going to do is we're going to look for key 11. We want to see, is there an 11 in that array? And we see that there is. There's an 11 at position 4. So the binary search method should return 4. Okay, so first we're just going to trace through the algorithm. We're going to state the value of low, mid, and high, and then how many calls to binary search by the time 11 is found. And we know it has to return 4. I mean, we can just look at it. Okay, so the first time, so I'm going to try writing it here. So 1, should I write it not in red? Isn't red supposed to be one of those threatening colors? Because because that's what we see, like, we've get points taken off. That's what I've been told. Okay, so 1, or maybe it doesn't really matter. Okay, so initially low is for the first round is always 0, and high is the index of the last array element. In this case, is 17 minus 1 or 16. And then your mid is halfway through. It's 16 plus 0 over 2, so it happens to be 8. So halfway through the array is in position 8 is halfway through the array. So we look at halfway through the array, position 8, which I think is 101. Yeah, so 11 is at position 4. So the 101 is at position 8. So in this case, list of 8 is, and the key is 11. So in this case, list of 8, which is 101. 101 is greater than 11. So we look to the left, right? So we can actually just cross all these out. And look how much we got rid of all those terms right away. And okay, so and now, so the second round, low, so we either change low or we change high, but never both. And so and high in this case, we're looking at positions 1, values 1 through 97. So your high is actually your high is mid minus 1. Right, it's 8 minus 1, which is 7. And now low plus high, so you get 7 plus 0 over 2. So your mid is 3. So we're using Java arithmetic. So 7 divided by 2 is 3. So now we look at position 3, and there's a 9 there. And in this case, list of 3 is less than the key. So list of 3 is less than the key. So because the array is sorted, everything to the left of 9 is less than the key. So for the next round, right? So for the next round, we're going to reset. We're going to look to the right of mid. So now your low is mid plus 1, which is 4. Your high stays the same. And now what's your mid? 4 plus 7 over 2, it's 11 over 2 is 5. So you're at position 5, which is 34. Okay, so now list of list of 5 is greater. Now so list of 5 is 34. List of mid, so your mid is 30. Your mid is 5. List of mid is greater than 11. So that means you look to the left, right? So if list of 5 is greater than 11, everything to the right of 5 is greater than 11. So we can actually cross out all these terms. Okay, so now we actually look to the left. So this is a 3 here, students. And then so for the next round, iteration 4, so we're looking to the left. Okay, so that means so the low is going to be 4, and now your high is going to be mid minus 1. So your high is 5 minus 1, which is 4, and now your mid, and the mid is 4 plus 4 over 2. It's just the average of 4 plus 4, and you get 4. So then in the next round, what you see is okay. So what you see is that you do one more round, and then let me see here. So low is 4. You see that you see both Boolean expressions are false, right? Just want to make sure. So your mid is 4, and so this is when we actually return 4. So the fourth iteration, low is 4, high is 4, mid is 4, and so then what we do here is we just calculate mid is high. So high and low were set to 4 in the previous iteration. Now we set mid to 4, and well, numbers of 4. So numbers of 4 is 11. The key is 11. So the two Boolean expressions are false. So we return 4. So we're done. So there's 4. There's 4. So we have all the lows and the highs for every call to binary search, and the answer to this is 4. There's 4 calls made. Yeah. So the first two calls to binary search, low is 0, and the second two, low is 4, and then for the first one, high is 16, then 7, then 7, then 4.